This is the 25th lecture or video on single agent search, on a course on single agent search. And in this video, we're going to be continuing from the last video, and we're going to be looking at how we are able to do these ranking functions or these mapping functions from a pattern database that we're building in memory that is a subset or an abstraction of our entire state space. And in the last video, we looked at how we could build a ranking function that ran in n squared time, where n is the number of elements in the permutation. And in this video, what we're going to be looking at is how we can actually do that for what's called a k-permutation, or looking at the first k elements according to our pattern database. So that's the first item we'll be looking at. And then we'll be looking at an algorithm for doing linear time ranking by Myrvold and Ruskey. And we will be looking at this briefly. And so I won't be showing how to use it for pattern databases, but I'll show you how the general algorithm works. It's not too much different than what I'm going to show you here for taking our lexicographical approach and using it for ranking pattern databases. So let's start with ranking pattern databases. And I'm going to start with something that might seem like it's an aside, but I want to look at what we have for a state. So let's suppose that we have some state. It really could be arbitrary state here. And I'm going to call this it's a permutation. So I'm going to call it pi. And it's going to be just some arrangement of values here. So let's do 3, 1, 2, 5, 0, 4. It could be anything that I want. And there's this idea that exists, given a permutation of the dual of that permutation. I'm going to write that as pi to minus 1 as being the dual. The dual has some really interesting properties, and it's an alternate representation. So at this point, what this representation says is this says 3 is in location 0. It says 1 is in location 1, 2 is in location 2. Whatever this happens to correspond to. So this could be, for instance, a 5 puzzle, a 3x2 sliding tile puzzle. And this would tell me where each of the tiles are. But there's another way we could represent this. We could represent this as not saying where each of the tiles are, but we could actually say where a particular tile is. So the dual is telling me, is this alternate representation? And what I'd be saying here is, tell me, and I'll write this just a little bit lighter underneath here. So tell me where the 0 tile is, where the 1, where the 2, where the 3, where the 4, and the 5 are. Okay, so we would look here and we'd say, well, the 0 tile is here, and that's location 0, 1, 2, 3, 4. So I'd put a 4 right here because that tells me the 0 is in location 4. Okay, and if I want to know where the 1 tile is, where the 1 is in location 1, the 2 is in location 2. The 3 is in location 0. Right, so 0, 1, and 2 there. The 4 is in location 5. And the 5 is in location 3. And so this gives us a representation, this alternate representation that tells me where a particular tile is. So this is the answer, where is this tile, as opposed to this is a location that tells me in this location you'll find this particular tile. And it ends up that duals are really powerful for making efficient algorithms. And we're going to need them both for ranking pattern databases and for our linear time ranking function for making this efficient when you actually do the computation here. And what we're going to do is, I'll talk about this here, but the one thing to understand here that's interesting, because there's actually other uses of this. So for instance, there's an algorithm called dual IDA star. And what dual IDA star does is it actually searches between the space of both the dual and the primal, or the regular representation. We can also do dual heuristic lookups in certain types of state spaces. There's certain properties you need to have. In particular, your actions can't be dependent on the location of a tile. So dual lookups and heuristics don't particularly work well in the sliding tile puzzle, but in something else like the pancake puzzle, if you were trying to build a pattern database there, then this is something where a dual lookup could work very well. And one of these things, what these are relying on is actually, if I were to take the permutation that took pi and converted it to be the goal, and then I applied that same permutation from the goal, it would put me in the state of the dual right here. So it's very interesting connections between what these dual means, how you get between them, the number of moves to get from the dual to the goal is the same to get from the original state to the goal, and other things like that. Now, suppose that I now am looking at ranking a PDB. And let's just say, we'll keep with the same example from up above. Let's just say that my state that I have, so we'll call that pi again, is something here, 3, 1, 2, 5, 0, 4. But I have a pattern. And the pattern that I want to use for my pattern database, so this is essentially my abstraction, is going to be that I'm only going to care about tiles, let's just say tiles, actually I'm going to make this interesting. So I'm going to say tile 0, actually, and tile 5. Okay, and I want to be able to say, look, I can care about 2 arbitrary tiles here when I want to do this computation. And so if I think about this, then what is going to happen? Well, if I tried to write down what I wanted to do here, like my state, so phi of pi, what I would get is I'd get, well, a star, a star, a star, then my 5, then my 0, and then a star. And the problem here is that when I think about trying to run my ranking algorithm on this, is how do I actually do this ranking? Because typically what we're doing is we start with the first element, and then we know how many permutations there are for the remaining element. Then we do the second element, and we think about how many permutations are there left for the remaining elements. But here, like, there is no first element here. And so for this, and what we could have is really, we can have any combination of values here. Could be the 0 and the 5, and they could be in any order. And so it's unclear how to actually say that this is what I want to rank here. But it ends up that what we can do is, if we look at what I want to look at is the dual of phi of pi. So the dual of this is going to be telling me not where the 5, not that we have the 5 and the 0, but what I have is I have the 2 items that are in my pattern. And in this case, there's 0 and 5. And so what I'm just going to write here is, where's the 0? The 0 is in location 0, 1, 2, 3, 4. And the 5 is in location 3. And when I compute the dual representation of a pattern database, where the dual is relative to the values right here that I'm wanting to use, then what I find is, for the dual representation, I'm always going to have actually as many values as the dual here, and I actually have a permutation here. And so what I would see, initially at least, and it depends on the way that I'm doing this, but if I look at this in particular, what I see is that initially this would just be, what is the radix here? Well, this is radix 6 and radix of 6, because each of these values have 6 possible values. And if I wanted to convert it to a mixed radix representation, then I would get 4 base 6, and I get also 3 base 6 here, because 3 is less than 4. Okay, so this gives me, oh, sorry, not 6, base 5. Okay. And so once I get into this representation, the mixed radix representation here, then I can write down what the ranking is, and the ranking is just going to be 4 times. And then what I want to know is, well, how many values are there possible here? Well, typically before we would have said 5 factorial, but because we're not representing anything lower than a 5, I'm going to divide that by 4 factorial. And then I'm going to have 3 is my next value there, times 4 factorial over 4 factorial. Okay, so this gives me the ranking of a pattern database. In order to actually do a ranking of a pattern database, what we need to do is we need to first use the pattern, convert the pattern to a dual representation, convert this to mixed radix, and then from the mixed radix, we can calculate the rank directly here. And just to do this in one more time here, so we'll just call this pi 1. We could now ask what pi 2 is, and I'm just going to make something up arbitrarily here again. And what I'll do is, on purpose, I'll reverse the order of the 0 and 5, just so that we can see what happens here. So it doesn't, in fact, well, actually, right, I'll just start with phi here. So we can really just say star, 0, star, 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 5. Did I get this right? 1, 2, 3. We'll erase one of those stars. There we go. 1, 2, 3, 4, 5, 6 values there. Okay, so here's a new value here. What I need to do is I need to compute the dual. And the dual is going to tell me where is the 0 and where is the 5. So the 0 is in 0, 1, and the 5 is in 5. So this is going to be 1, 5 here. And when I convert this to a mixed radix representation, then I have 1 base 6. And now my 5 is going to become 4 base 5. And so the rank of this state then in my pattern database is going to be 1 times 5 factorial over 4 factorial plus 4 times 4 factorial over 4 factorial. Okay, so what that gives us is for a pattern database, we see how if we understand what the dual is, we can use the dual to take our pattern and convert it into a set of locations. When we get this compact set of locations, we can convert this to a mixed radix format. And when we get the mixed radix, then we can directly compute the rank of a particular state. And again, we can notice that I don't actually have to do this explicitly, like take a state and actually star out these values or something like this. I can just look up where is the 0, where is the 5. When I look up where each of those are, then I can, and actually we can do this, we can basically build the dual, and we can do this dual in linear time. Then we can ask for the values that are in my pattern. I just ask where they are, and I'll use that as the coefficients here to the terms that I get here for computing the rank of a particular state. So hopefully this is not too hard, but given that you understand what we did in the last lecture, but actually getting to this step, if you go and read a paper about pattern databases, they won't necessarily step through some of this process. And so, or maybe it may be difficult to find where they're going through that. So I just want to make this as clear as possible so this is easy to implement. And this is what you're going to do. For my students in the class, they're going to have to do this for the homework assignment. Now, what we have here is we still, when we look at the ordering of the ranking function of the states that we get out, we're still going to get them in a lexicographical ordering. And that means that there's sort of a dictionary sorting on the elements as we run through them. And if we're willing to give that dictionary ordering up, and well, I'll talk about that for a second, but if we're willing to give it up, we can get a faster function for doing our ranking. And whether we need a faster function or not sort of depends on things like what is the size of my pattern. But if I needed a faster way to do this, so the dictionary ordering, the reason when we might want a dictionary ordering is it might increase the locality of our state space. So when we think about like an external memory algorithm, external memory algorithms, oftentimes like 2-bit breadth first search relies on having high locality so that the neighbors of a state are nearby. And so I'm hoping that most of my neighbors are able to be processed locally, and therefore I don't have to write as much to disk. But if I don't want to have to do that, or don't have to worry about that, then if just the cost of this is going to be too expensive, we can move to an alternate approach. And the way this works, and I think this is it's a fantastic algorithm. It's really, it works really well. And it has an intuition, and actually it comes from the idea of what happens if I wanted to take a permutation of elements and I wanted to get a random permutation. And so something you might be tempted to do is like, well, just randomly swap a whole bunch of items, sort of akin to shuffling a deck. But that won't necessarily, depending on how you do it, it won't necessarily give you a good shuffling of items. And the actual algorithm that does this effectively is to say you take a random item and you put it at the end of the array, and then you randomize the remaining items except for the last one. And that guarantees that every item will be chosen at random with equal probability, and you'll, with equal probability, get every possible permutation. And what we can do is basically that random number process of choosing a random number, instead of like having the random number come from actually like a random number generator, we're actually going to have what we use for that random number computation is our ranking function itself. And so we're going to do this first. Mostly I've been talking about this ranking where we get a state as input. So we have a state, we compute the abstraction, and then we get the mixed radix, and then we get the number coming out. So this is ranking because we're going from a state to a value. We're going to talk about unranking first, where I take a value and I go back to a state. And then once we've seen that, we'll see how we can go from a state back to a value. So this is a linear time unranking. And how does this work? Okay, the way that this works is what we're going to do is we're going to assume we have a rank that we want to unrank. So we know how many items there are or how many permutations there are, and we're just going to choose a value. So let's say my rank is going to be 81. And let's just say that there's 5 elements in my permutation. And then let's say that what I have here is I have a permutation. I'm going to start it out as a sorted permutation, 0, 1, 2, 3, 4. And what I'm going to do is I'm going to randomize the items here, except I'm going to randomize them using my rank as my seed, or sort of as my random number. This is where I'm going to get my random numbers from. So basically I'm going to say, look, if I have a rank of 81, I want to get a random number, 0, 1, 2, 3, or 4, that I'm going to use to randomly put my first item at the end of the array, because that's what this randomization function does. And so the way that I do that is I just take 81 mod 5, and that's going to give me 1. And so that tells me I want to take the first item in the array here, and I want to swap it with the last item, because I'm just choosing a random item to put at the end. And then because I've used up, in some sense, I've used up the bottom 4 values underneath here, or the bottom 5 values, sorry, 0, 1, 2, 3, 4. So I've used up the bottom 5 values. What I'm going to do is when I do the remainder of my calculation, my next rank in the next step is going to be 81 divided by 5, because I've used those up already, which is going to be 16. And what I'm going to get here is I get pi. So I'm going to swap the 2 ones I have there in red. I get 0, 4, 2, 3, 1. And this is going to be, I've chosen the first item at random. So this side is randomized and this side isn't yet. And now I'm just going to continue to randomize the items on this side here. And instead of using 81, because I've used the bottom 5 values, now I'm going to use the number 16. So if we look at 16, if I treat this as my random number, when I do, the other thing I have to be aware of is that the number of items that are left to randomize has now gone down to 4. Okay. So if I look here, then what I see is 16 mod 4 is equal to 0. And 16 divided by 4 is equal to 4. And so what I'm going to be doing here is I want to take the 0th element and I'm going to swap it with the end at this point, which is the 3. And so that's going to give me a new permutation, which is 3, 4, 2, 0, 1. And just to be clear here, the 0 and 1 are now the items at the end, which have been randomized, and these ones haven't. Okay. So now we can continue this procedure. Now we're going to be starting with a rank is equal to 4, n is equal to 3. And so when I do 4 divided by 3, my next value is going to be 1, and 4 mod 3 is equal to 1. So in the next step, I'm going to be swapping item 1 with item 2. And that gives me my next permutation as being 3, 2, 4, 0, 1. And at the very last step, what I'm going to do is I'm just going to finish this process. So now I have a 1 here. My n is going to go to 2, so my rank is equal to 1 and is equal to 2. And so 1 mod 2 is equal to 1. And that tells me I'm going to swap the first element with what number? Well, I'm actually swapping the first element with the first element. And so that tells me actually, in the last step, the first element will just be what it is. So my final answer here is 3, 2, 4, 0, 1. Okay. So if you understand the algorithm for randomizing an array of elements by taking a single item, a random item, moving it to the end, and then from the remaining items, a random item goes to the end, and you just repeat that procedure. And the way we get our random numbers is we use modulo on the rank that we're trying to unrank. So we're trying to go from this index back into a state. And trying to go from an index back into a state, at first there's 5, then 4, then 3, then 2. And at the end, there's only one element. Oh, did I write that wrong there? This should be 3. I get back to my actual state, 3, 2, 4, 0, 1. So that's essentially just running that randomization algorithm using my rank for my random numbers. But because I'm basically always doing that in the same way, then I'll always get the same answer. You know, I'm not doing any randomization here. And what you could see is that with every possible rank over all the possible ranks, then I would get every possible, you could go through here and show fairly easily that you'll get all possible permutations of these items. And so we will get all of these will be equally likely. So this only takes linear time because we just run through here one time. We randomize, move to the end, randomly move to the end, randomly move to the end. And so we're in good shape there. And so as I said earlier, this is a paper by Myrvold and Ruskey that describes all of this. And they have pseudocode for doing this in their paper. I will see if I can add a link to it to the description down below. And then I just want to show you how we reverse that process. And I'm not going to show you every step here, but I want to say that in order to reverse the process, we have to be able to look up and say, where is a number? Where is a number? And that question of where a number is actually the same thing we needed here, which is the dual. So I'm not going to write out the dual explicitly, but in the algorithm I'm going to show you, it can be done very efficiently because we can calculate the dual efficiently. And so that's what's going to make this work well. So now what we want to do is rank. I'm just going to go on the next page. So we want to rank 3, 2, 4, 0, 1. And how are we going to do that? What we're going to do here is what we want to do. So a ranking is, I'm trying to get this numerical value back out. And so here I have an array that is unsorted. And what I'm going to do is I'm going to sort it. And as I sort it, I'm going to get a set of values out. And as I get that set of values out, then it's going to tell me what the computation is. Okay, so what we're going to do is we're going to ask, the first thing we're going to ask is, where is the maximum value? At this point, we're looking for 4. 4 is the maximum value. I can use my dual to do this efficiently. And I'm going to say, look, I'm going to take 4 and I want to put it into the last value in order to sort the array. And what I want to know is what is the value that was there previously. And so I'm going to write that down over here. This is 1. 1 was there previously. And what I'm going to go to is I'm just going to swap those 3, 2, 1, 0, 4. Okay. And now I'm going to ask, well, what I want to do is I want to keep sorting this. So I need to put the 3 in the next element. And I can use my dual to say, where is the 3? And I'm going to ask, what is here currently? And the answer, what here is here currently, is 0. And I'm wanting to swap the 3 and the 0. Okay. And so I swap those, and what do I get in my next step? Well, I get 0, 2, 1, 3, 4. Okay. And now I want to say, in the next step, I'm going to say, look, I want to put the 2 in the next value. So I'm going to take the 2 and I want to swap it with whatever value happens to be there. And this is really interesting. The 1 was there. 1 has really gotten in the way. 1 was in the wrong place in the first step, and 1 is in the wrong place again here. But I'm going to swap those into place, and I'm going to get 0, 1, 2, 3, 4. And the next step that I want to do, at the end, everything is going to always be sorted, but there might be the wrong value inside here. But I see that no, 1 is in the right location. And so, well, 1 does happen to be there, though. So here's the 1. Okay, so these were the values that were in the location that I swapped with as I went down, 0, 1, 0, 1, 1. And I can use those values to actually get my ranking function. And I'm going to now write out what the equation is here. And what it is this. It's going to be 1. So remember, there's 5 values inside here. So this is 1 plus 5 times. And then I have, so the 1 was coming from here. Now I'm going to take the 0 from here. 0 plus 4 times. And then I have a 1 from here, plus 1, times 1 plus 3 times. And then I have another 1. Where did I get this little line there from? Okay, so that's there. 3 times 1 plus and then this is just going to, I have a factor of 0 here. We're always going to end up with a 0 at the end. Okay, so what's going to happen is my first value of 1 comes from here. My second value of 0 goes right inside here. My next value of 1 comes from right here. And my last value of 1 is going to go right inside here. And whatever's left over, because at the end, we're always sorted. The last item is always sorted, so we're always going to have basically a 0 sitting at the end there. And so we don't have to worry about what's there, and we don't even have to multiply by, I mean, this in theory would be 2, right? 5 times, 4 times, 3 times. In theory, there'd be a 2 times here. But that's always going to be 2 times 0. And what we're going to see here, so what do we have? We have, if I just do the math, it's a 1 times 3, so that's 3, plus 1 is 4, times 4 is 16, times 5 is 80, plus 1 is 81, and so this is equal to 81. And if we remember back here, when we did this process, 81 was the original rank that we started with. And so what we see here in this linear time algorithm is we can reverse the process that we used to do our ranking, which was this randomize an array. So here we have the fully randomized array. And here what we're going to do is we're going to say, well, take the ranking I start with, and essentially what I want to do is sort it. And in the process of sorting it, then I'm going to construct this, I'm going to construct the rank out of this, where, you know, I've got these coefficients, which essentially are giving me factorials. If these numbers were all multiplied out, you'd see that there were factorials there. That are being multiplied by through, and this is going to give me the final rank that exists here. So you will find, if you were to go, for instance, into the original paper, you'll find this is called the rank 1 function. You'll find the pseudocode there for how this function works, but it's based on this idea of sorting and randomizing arrays, and so this is a more efficient way to do a ranking function. So hopefully this was understandable. I did this whole lecture a little bit fast. I wanted to finish off some of these details here and go through them in a little bit of detail without taking too long. But hopefully you're able to understand the exact computation that goes into building a PDB now. And then also if the ranking and unranking are expensive, then we do have this linear time function that we could use here. And so now with this, we have sort of the key pieces put together of how to start building heuristics that come from these abstractions of our state space. And that's going to be very powerful. And we'll look at quite a few techniques that can be used on top of these to make these heuristics to be even more powerful. And so we will continue in the next lecture with more of those details.